everyone, let us study functions of single random variables in this video. Let us consider a random variable x whose PDF and CDF are known to us. PDF is given by fx of x, CDF is given by fx of x. Now we define a new random variable y which is a function of x. For example, let us define y is equal to 3x plus 4, or it can be y is equal to 6x square. So we are defining a new random variable which is a function of x. And we say that the input random variable has undergone a transformation when we are able to predict the PDF of the output random variable using the input random variable x. Let us take one example. Here x is an arbitrary random variable whose PDF and CDF are known to us. Let us define a straight line equation, linear equation, defined as y is equal to ax plus b. This straight line equation is shown here. You can observe here A is a slope which is positive and monotonically increasing, and b is a constant which is the intercept, and you can see that this is equal to b. It represents the intercept. Now we can find the inverse function of this by x equal to y minus b by a, and we assume that a is greater than 0 because we have assumed the slope to be positive. So you can observe here we have two regions we can define here. One region is where x value is less than x, because all these values are x values, and this region is x less than x. This region we call it as x greater than x. Then similarly we have two regions. This region is y less than or equal to y, and this region is y greater than y. For a given y, let us identify the region along the y-axis where y value is less than or equal to y. That is, the region is this. Using the inverse function which we have defined it in the earlier slide, that is x equal to y minus b by a, let us try to identify the region along the x-axis where x value is less than or equal to x, that is this region. Substituting x is equal to y minus b by a, we have x value less than or equal to y minus b by a. Let us try to do the transformation. That is, we try to get the CDF and PDF of y with respect to the random variable x. So that can be done. CDF for y is defined as fy of y is equal to probability of y less than or equal to y. Let us make use of principle of conversion of probability. Then we define fy of y is probability of y less than or equal to y is the probability of x less than or equal to y minus b by a. That is equal to fx of y minus b by a. Differentiating this CDF with respect to y, we can get the CDF. So let us define fy of y is equal to 1 over a, the PDF of x, y minus b by a. Let us take this problem. It is given that the random variable z is Gaussian with a mean of 0 and variance of 1. The random variable y is obtained from z with the relation y equal to 3z plus 7. We need to find the PDF for y. So the given data is, first data they have given it is the Gaussian distribution. So they have made use of Gaussian distribution. Then second data they have given is mu z is equal to 0. Then the variance, that is standard deviation whole square, is equal to 1. And next data they have given here is y equal to 3z plus 7. Therefore, you have z equal to y minus 7 by 3. So we'll make use of the formula to calculate the PDF for z, that is given by fz of z is equal to 1 over root 2 pi sigma z exponential of minus z minus mu z whole square divided by 2 sigma z square. Let us substitute mu z as 0, sigma z square as 1 in this equation. Then it gets simplified to 1 divided by root 2 pi exponential of minus z square by 2. Let us define the PDF for y. PDF fy of y is given by probability of y less than or equal to y. Now we know that we can define it is the probability of z less than or equal to z. That is, here it is given as y minus 7 by 3. So that is equal to fz of y minus 7 by 3. Now, fz of y minus 7 by 3 is given by 1 over root 2 pi e to the power, that is exponential of minus y minus 7 by 3 whole square by 2. That when we simplify this, you get this as root 2 pi exponential of minus y minus 7 whole square, 9 into 2, that is 18. And we can get fy of y by differentiating this with respect to y. That is, when you differentiate this with respect to y, we get 1 over 3 fz of y minus 3 by 7. Let us substitute fz y minus 7 by 3 using this expression. We get fy of y. That gives you 1 over 3, 1 over root 2 pi exponential of y minus 7 whole square by 3 divided by 2. It simplifies to the form 1 by 3, 1 divided by root 2 pi exponential of y minus 7 whole square by 18. Let us take the second example. Here we have considered x as an arbitrary random variable, and we are defining a function y as a function of x. That is, y is equal to ax square, and it is assumed that a is greater than 0. When you plot it for all values of x, we get the y like this. Y is equal to ax square. And inverse function can be defined for this, and that is given by x square is equal to y by a. So therefore x is equal to plus or minus root y by a. So we can define two regions. One region is x greater than 0, other region is x less than 0. The region x greater than 0 is defined like this, and for x less than 0 is defined like this. So therefore your x value will vary from minus root of y by a to plus root of y by a. So we can define the region for y-axis. We have considered only positive values, and this region is here, where y value is less than or equal to y. So we can find the PDF. PDF is given by Fy of y is the probability of y less than or equal to y. So here the probability of x, it varies from minus root of y by a to plus root of y by a. So we can write this as it's the PDF of root of y plus y by a minus the PDF of minus root of y by a. By differentiating the PDF, we can get the PDF. When we differentiate this with respect to y, we get this as 1 divided by 2 root of ay fx of plus root of y by a, PDF of x minus. We have to differentiate this with respect to y. We get that as minus 1 divided by root 2 divided by root of ay. That gives you the PDF of fx of x multiplied by this. Let us move on to the next topic, condition random variable. Following steps are needed to condition the random variable. First step, the random variable x is defined. That then we need to find the PDF of that random variable x. Let us consider an example where I toss the coin twice. When I toss the coin twice, the outcomes can be defined as head head or tail tail or head tail or tail x. Let me define the event. Event is I want both the times when I toss the coin, same face to appear. So in that case, I have here two events, that is head head and tail tail, because I want, when I toss the coin, I want both the faces to appear the same. So here I can define the PDF. So PDF is out of 4 outcomes, only 2 are eligible, are expected outcomes. So fx of x is equal to 2 divided by 4, that is equal to half. So this is what is shown here. I have a event, I have a random variable x whose fx of x is defined. Let it be like this. Now let us take the second step, that is some event b needs to be defined, in which the observations of x can be favored or it can be suppressed. So for example, I put a condition that whenever I toss the coin, I want only the head to appear. I don't want any other. When I toss it twice, both the times I want the head to appear. Then in this case, I am left with only HX. So I am defining a new event B, wherein I want only the head to appear when I toss the coin. Finally, third step, it wants to define a new PDF which says that f x given b or x condition b. So this one, this symbol stands for given, or you can even call it as condition. So in the next step, we need to define a new PDF, which is the f of x given b of x or x condition b of x, reflecting the conditioning effect of b. For example, for this particular problem, if you see now, f x condition b or x given b of is given by out of 2. Here, if I out of 2, I have only one possible condition. So therefore, it is 1 divided by 2. Same way, we can even define the PDF, because all the features of PDF defined for random variable x is defined even for fx given b. Now, graphical representation, if you look at here, if you have fx of x here, and in that a portion between x1 to x2 is defined by the event b. So that's why probability of b is this shaded area. Now, when you want to find f x given b of x, that is given here, and this area should be area under this should be always equal to 1. We have already defined conditions with PDF in the previous slide. Now let us try to define the condition PDF, and it is given by f of x given b of x is equal to probability of x less than or equal to x intersection with b divided by probability of b. We have here 3 regions we can consider. One less than x1. In that case, there is no common intersection area between b and x less than x. Then it is going to be b. Then we have here that is a common area between x1 and x2. That is the common area we have. So third one, we have to consider this area. So for this area, for all the values of x, anywhere, if I take this is the point of consideration, any value less than x, if the common area is going to be b itself. So that's why it is written as b. So let us define the condition PDF. F of x given b of x equal to 0 for all values of x less than x1, and for any value of x between x1 and x2, it is defined as the ratio of fx of x minus fx of x1 divided by probability of b. For any value beyond x2, say somewhere here, then its value is always equal to 1. We can obtain the PDF by differentiating the PDF. So fx given b of x PDF is also given by the differentiation of the PDF, and that is defined as fx of x divided by probability of b between the period x1 and x2, and it is 0 otherwise. And once we know the PDF, we can find the mean. Mean is mu x given b is equal to integral of x PDF dx. Similarly, we can find out mean of k, that is expectation of x square given b is integration of minus infinity to infinity x square PDF dx, and variance can be found out, that is sigma of x given b whole square is equal to integral of x minus the mean whole square PDF dx. Some of the examples, practical examples are a PDF for noise in a communication system might be different if thunderstorms are present rather than when the weather is clear. Second example is in critical applications in electronics, two resistors may need not be matched. The event that the resistors are matched would then make the gain of an amplifier have a smaller variance than without matching. Let us take two examples to understand the condition random variable in a better way. For first example, we consider a case of rolling a dice. We know that a dice has 6 faces, so faces being tossed up, maybe 1, 2, 3, 4, 5, 8. It's any one of them. Let us define an event where number of even faces being tossed up. So here it is only 2, 4, 6 possible. So therefore we can define the PDF fx of x is equal to, it is 3 outcomes out of the possible 6 outcomes. So 3 divided by 6, that is equal to 1 by 3. Now let us define one more event B, where we want the number of prime number faces being tossed up. Now prime numbers, we know that among these numbers, prime numbers are 2, 3 and 5. So 2, 3 and 5. Now between event X and B, we have a common factor that is only 1, that is 2. So therefore we can write the PDF fx condition B or fx given B of x is equal to 1 out of this 3. So 1 divided by 3. We'll take the second case, tossing the dice twice. Let us define x as a random variable where number 2 of d1 facing up. If you look at here, that is d1 facing up, we have only here 6 uh, 6 outcomes are possible, and totally we have here 36 outcomes. So therefore PDF fx of x is equal to 6 divided by 36, that is 1 by 6. Then G is the number of cases where d1 plus d2 is less than or equal to 5. So here we can all those places where we have yellow colored ones, they are the ones which represent B. So 1 plus 1 is 2 less than 5. Similarly 1 plus 4 is 5 less than or equal to 5. 2 plus 3 is 5. Now similarly we have 3 plus 1, 4 plus 1. Total outcomes are 10, but we have to satisfy both x as well as b. So the common area is only 3. So therefore we can write it as 3 divided by 10. Let us try to solve some problems. First problem, our Gaussian random variable x has a mean of 75.1 and a standard deviation of 10.2. Evaluate the probability of x varying between 59.9 to 81.75. To solve this problem, please refer the appendix B given in Probability, Statistics and Random Process for Engineers by Richard H. Williams. This is a prescribed book, and in that book you go to the appendix B. There they have given you a table, values of normalized Gaussian PDF for different values of probability, for values of Z. From that table, using that table, we need to find the value of phi of Z, that is PDF. So we have first case, phi 1 of x1 minus mu x by sigma x. Here x1 is given as 59.9 and mu x is given as 75.1. Sigma x is given as 10.2. When you simplify this, you get this as minus 1.4902. So it is phi 1 of minus 1.4902. Second case, phi 2 is x2 minus mu x by sigma x. So phi 2 is equal to 81.75 minus 75.1 is the mu x value. Sigma x is 10.2. When we simplify this, you get this as 0.6519. So you make use of the table. So first let us try to find out phi 1 of 1.4902 using the table. You get this as 0.9319, and phi 1 of minus 1.4902 is given by 1 minus 0.9319, that is 0.0681. Similarly, we need to find out phi 2 of 0.6519. It is not defined in the table. So therefore, we have to find out the phi2 of 0.65 from the table. You get this as 0.7422. Then we have to get this phi2 of 0.66, that is 0.7454. Using these 0.65 and 0.66, we'll try to find the value for 0.6519 using the linear equation. So you have 0.7454, what is 0.66, and 0.65, it is 0.7422. This will define as the slope, and we'll try to find the phi value for 0.6519 by using the 0.7454 minus x, this is the unknown quantity, by 0.66 minus 0.6519. That gives you 0.7428. So therefore, you get phi2 of 0.6519 is equal to 0.7428. So we'll subtract, in order to find the probability of x varying between 59.9 to 81.75, we need to subtract phi2 of 0.6519 minus phi1 of minus 14902. That gives you 0.6747. We try to solve the second problem. A production drawing specifies the dimension on a printed circuit board as 0.75 plus or minus 0.02 centimeter. Assuming that the process that the manufactures the devices is such that the dimension is a Gaussian random variable y, and that the manufacturing process is slightly inaccurate. Mu y is the mean is given as 0.7505. Assuming that the precision of the manufacturing process is such that the standard deviation is sigma y is equal to 0.0014. What percentage of the printed circuit boards have the dimension within the specified tolerance limit? So let us try to solve this. We'll define a probability of y varying between 0.748 to 0.752. That is, this value 0.748, we have got it from 0.75 minus 0.002, and this value is 0.75 plus 0.002. So we'll try to get the phi value, phi of 0.752 minus the mu y, that is 0.7505, divided by sigma y 0.0014, minus the phi of 0.748 minus mu y, that is 0.7505, divided by 0.0014. That gives you phi of 1.0714 minus the phi of minus 1.7857. Now we have to make use of normalized Gaussian table from Appendix D of book Richard H. Gilliam, book on probability. Let us make use of the table to find 1.074. So from the table 1.07, we get the value 0.8577. For 1.08, we get the value 0.8599. So we'll make use of the linear expression and we'll try to get phi of 1.074, that is equal to 0.858. Similarly, let us try to find phi of minus 1.7857. For that, we have to find out plus 1.7857. So for 1.78 from the table, we get this as 0.9625. 1.79, we get this as 0.9633. And substituting the values in the linearized equation, we get the value of phi of 1.7857 is equal to 0.9629. But there is a negative sign, so therefore it is phi of minus 1.7857 is equal to 1 minus 0.9629, that is equal to 0.0371. So therefore we can write probability of y varying between 0.748 to 0.752 is equal to 0.858 minus 0.0371, that is equal to 82.09%. This will complete your module number 1, but I have put 2 videos wherein we will be solving more problems on a single random variable.